So this is the instruction set for my CPU. I have the basic logic gates. Um, I have a branch of equal to and branch of greater than instruction, and also a load immediate that loads a 6-bit value into any register. Even though this is an 8-bit CPU, I couldn't fit a 8-bit value in the immediate because of the constraints of the ISA. So as you can see, I have 4 bits for the opcode, 3 bits for the register addresses, for the arithmetic and logic instructions. Then for the branch instructions, I have a 6-bit branch address because I have 2 to the power of 6 program lines. And the load immediate has a 6-bit immediate stored in a 3-bit addressed register. So this is a small multiplication program I wrote for this CPU. So line 1 loads a 0 into register 3. Line 2 loads a 1 into register 4. Line 3 loads a 2 into register 2. And line 4 loads a 3 into register 1. And as you can see, I highlighted 6 bits of line 3 and line 4. Those are the inputs to the multiplication. So R2 and R1 contain the inputs to whatever multiplication you want to do, and depending on what you set those 6 bits to, the CPU will do a different calculation. So now we enter basically the loop that does the repeated addition. First we have R2 minus R4 and stored into R2. So you're basically just decrementing R2. Then there is a no-op because due to this being a pipeline CPU with absolutely no hazard protection, the register 2 will not actually be written to if the next instruction, which uses register 2, would come immediately after. So you have to put this no operation instruction before the next instruction because the next instruction uses register 2. So line 7 is a compare instruction, and it compares our register 2 to a 0, and that compare instruction sets the branch flags. Line 8 is the branch. It branches to line 5 if the compare results in an equals. And after the branch, you have add our register 1 to register 3 and store to register 3. So that is the actual addition that is in the loop. Now, you might be thinking that it's not in the loop. Clearly, I'm doing a branch before I am doing the addition. But what happens in a pipeline CPU is you load instructions while you're doing the previous one. And so the branch is loaded and then it begins to be resolved, but then before it's actually resolved, the next instruction is loaded and begins to execute. And I do not have any system for flushing instructions that have been loaded if the branch, even if the previous branch is taken. So I put the addition after the branch because it will still always be executed. So in a sense, it is still inside of that for loop. So now let's actually see this multiplication program in practice. So I already have the CPU loaded onto the FPGA. Now we just have to input the program. So in order to have an input and a run function on this FPGA CPU, I use the joystick as a sort of input to a big state machine. So right now, it is in the state of selecting which line of code to edit. So for example, if I click up, it will go to line 1, up again, line 2, up again, line 3, down, line 2, down, line 1, down, line 0. And so you might see that here I only have 8 switches. However, my instruction length is 13 bits. So I again use this state machine to divide the program input into two sections. So, for example, in our program, the first line is 101 followed by 8 zeros and then 1 1. So the right eightmost bits, the 8 rightmost bits, are 6 zeros followed by 2 ones. So what I would do is I would turn those two switches to ones, and I would click to the left, inputting that section of the program. Now I can input the second section of the program, which is starting from the right 0 0 1 0 1, and click to the left again. Now we can see that we have the instruction 1403 stored in program line 0. Now if I click up, it goes to line 1. So now I can input the second line of my program. So it has 0 0 1 1 input, and then it has 0 0 1 0 1 input. So now in line 1 of the program ROM, I loaded 140C. Click up again to input the next instruction. And now I'm going to speed up the video, as you probably got a good idea of how to input the program, and I'll see you in a bit. So now we can go through and see if I inputted the program correctly. So line 1, 1403, line 2, 140C, line 3, 1412, line 4, 1419, line 5, 0EA2, line 6, 0, line 7, 0E80, line 8, 1204, and line 9, 0C5B. Now in order to run the program, all I have to do is click to the right, and it will start calculating the multiplication, in this case 3 times 2. So the output will show up on the LEDs, and basically how the output works in this situation is register 3 is just mapped directly to the LEDs. So whenever the lights stop shifting, you know that that is the answer. So if I run it, so you can see that we have 0, 0, 0, 0, 0, 1, 1, and 0, which is 6 in binary. So 3 times 2 is 6. In order to stop the execution, I just have to click to the left, and now we can edit the program again. So for example, I can go back to line 4, and instead of doing 3 times 2, I can do 4 times 2. So if I go to line 4 and change it to 1 0 0 0 0 1, input, and then 1 1, you can see that the input is now 1421. The instruction is now 1421, which is store 4 in R1. Now if we run it, you can now see that the answer is 0 0 0 0 1 0 0 0, which is 8 in binary. So this is really nice because you can basically debug on the board. You can just go back to your program, edit it anywhere you want to, and run it again and see what happens. So Thank you for watching. I thought this might be pretty cool. So leave a like if you liked it. Leave a dislike if you didn't like it. And thank you.